Hi, everyone. My name is Kevin Bone, and for my master's project in the GIST program at the University of Arizona, I'm going to talk about the interactive tool I developed to identify potentially flood-prone areas using the Topographic Wetness Index. So, understanding areas that are susceptible to floods is important to land use planning, construction development, emergency management. Hydrologic models that would typically be used in flood hazard mapping can take a lot of data, stream flow records, precipitation data, actual on the ground survey data, and they can also be pretty complicated. They take a strong engineering background, but GIS can still be used to create rapid flood hazard assessments. While the outputs are less detailed, they can also require less data and time and still have hopefully useful results. Oops. So one GIS approach quantifies how the terrain influences runoff and water accumulation by calculating the topographic wetness index. So if we were trying to determine, how much water could accumulate at this point circled in red here, it would depend on the upstream area contributing flow to that point. Let's call this a medium amount. The cardinal or diagonal flow direction through that point, so down the slope, as well as the actual slope value at that point, so pretty steep. So we'd expect this point to have a pretty low TWI value, as opposed to maybe down where these streams converge, where we would have a larger accumulation area, more gradual slopes, so we'd expect maybe higher wetness values here. And so the TWI has been widely used from identifying local drainage issues to looking at more regional flood risk vulnerability. And not only is it trying to quantify water accumulation, but it also correlates with soil moisture levels. So it's also been used for agricultural suitability analyses, species richness, as well as wetland identification. And so one advantage of the method is that the only required input is a digital elevation model, which you can download for anywhere in the US from the USGS application called the National Map. But there are a lot of different products available and available in different resolutions, so it can get a little confusing if you don't know a whole lot about it. LiDAR versus IFSAR, meter resolution versus arcsecond resolution. What does that exactly mean? So for a typical user here, they're going to go to the website, draw in their study area. Then you kind of have to click through this list one by one to see, are these tiles in my study area? Do I actually want to download them? So it works clearly, but I think there's some room for improvement there in terms of ease of use. So that is where my project comes in. The main objective was to develop a Python tool to identify flood-prone areas using the TWI. I wanted to adapt existing tools, and just pull out the key functionality from those. The USGS does have their own ArcGIS toolbox that you can query a lot of their products, but there's a whole lot going on there. So I just wanted to kind of strip out the key parts to automate that DEM download. And really, I wanted to, pack as much functionality in the tool itself so that you don't have to go outside the tool to look for more data, find additional functions. And so the other goal is to really streamline it as much as possible, make it as easy to use for the target audience of land use planners without much programming experience. I didn't want to just create like a long Python script that runs all at once, since it can be hard to figure out the errors. I didn't want to just have a black box approach, put in your input, take the output without really knowing what's going on. So that's why I chose to develop a Jupyter notebook, which runs Python code in single cell blocks at a time. I wanted the user to interact with it, to make choices, to be able to go back and repeat steps. Jupyter notebooks can have markdown cells with text, explanatory text, images, links to more info. So really, I want it to be an educational tool. I want the user to understand what they're doing, but also understand what the tool can't do. And so finally then, to demonstrate the tool functionality, I compared the outputs to some known flooding issues at a study area. So let's get into the workflow, which broadly has 3 steps. I don't want to go through all the code here, but I did include some pseudocode segments here just to kind of see the type of things we're working with. So this first step is all about, again, acquiring that DEM data. So this first section here would be a markdown cell. It would provide a link to this website. You click it, it pops up. You draw your study area, and then in the next cell, it'll prompt you just to paste in those coordinates straight from the website. It takes the user input as variables. It'll then query the National Map API and bring out a list of all of the latest DEM tiles that are available for that study area. And so then it will download them all, mosaic them together into a single raster, project it into whatever coordinate system you want. And in general, I included, print statements along the way, so you can see exactly when something finishes. And so it makes any errors pretty easy to identify because you know exactly which cell they came from. The second step calculates the TWI value using ArcGIS spatial analysis tools. Really, this is kind of the most straightforward part of the code itself, so I didn't want to include any here. It uses the derived continuous flow tool to calculate the flow directions and the flow accumulation values, without needing to identify and fill sinks in the DEM first. It also uses the surface parameters tool to calculate the local slope value of each cell. And then after some conversions and adjustments to make sure there are no undefined values, it calculates the raw TWI values as the natural logarithm of the flow accumulation divided by the tangent of the slope. And so in this step, really the user is mainly naming the outputs. But there's also lots of explanatory text, better than I'm giving now. This is what this step does. Here's a link to the tool itself if you want to find more information. And so the user can stop here and call it a day if they want. But step 3, I would say, is where the fun's at. So in step 3, all the steps are optional, which makes this diagram here kind of tricky to draw. Every output can then be fed back as input to another process or skipped entirely. The intent is really to be able to use the results however you want, whether that's further data analysis or just visualizing the results. The raw results can have kind of a lot of inherent noise present, especially when using high resolution data. So one option is to apply a low pass filter to kind of smooth out the results using focal statistics. And when you calculate the TWI, the range of values is going to be different for every study site. Typical values would be like -5 to 30. So the exact value of a cell is less important than the overall distribution of values. So this middle step can normalize values from 0 to 1 to kind of help make comparisons between different sites. And the steps on the right are all about different ways to classify and symbolize your results. And this is really where that kind of local knowledge of your study area can come into play, because the tool calculates the TWI for every cell in the landscape. So ideally, you need some way to verify what actually constitutes as a high value, a high wetness value. So maybe you have field data collected from known flood extents, or maybe you take this and do some kind of cluster and outlier analysis. And so then if you kind of find that threshold value, the tool can reclassify the raster based on that threshold value. So then you get a binary of low values, high values, and you can choose not to symbolize those low values. And then once you are satisfied with everything, you can save that out to a layer file to preserve all that symbology. And then you can add it to a 3D scene, which I think is fun to help visualize things. And here, this kind of bottom chunk, you can add some vertical exaggeration to the scene, which I think really helps kind of visualize how the results would interact with the terrain. So that is enough code here. Let's see how we could actually use this. So Lake County is a rural county in southern Oregon. It doesn't seem to have a lot of issues with large flooding events. FEMA actually doesn't publish flood hazard maps in their online layer. So you can only download them as paper maps. And so the last official floodplain mapping study is older than I am. So, but they can still experience, flooding issues on a more local scale. I really just want to focus in here on one area in town for the sake of time, in the town of Lakeview. So during heavy rains and spring snowmelt, water and even boulders can wash down from the Boulder Canyon to the east, kind of affect these streets on the east side of town. But then also, if we look where this marker is on Roberta Road, this road has been needed to close several times because there's an existing ditch here and a culvert that passes under the road. And so that's been known to back up and cause standing water on the road. So basically, I took the TWI tool and ran it at two different DEM resolutions, 10 meter and 1 meter, to kind of see if they provided enough detail to highlight any of these flooding issues. So let's get into that. Hopefully this is visible enough on your screen. I'll slowly give you a little sneak peek of the 1 meter results here. But first, I will slowly drag it over to the 10 meter results. So the tool downloaded 6 DEM tiles to calculate the TWI for the entire Lake County. And the results were rescaled here from 0 to 1. And then I think it was really critical deciding what data classification method to use here to symbolize the results. And so I kept it at equal interval just to kind of the distribution were kind of skewed towards higher values. So I think equal interval kind of helped highlight where these high values are. And we can see how maybe water could potentially accumulate here through town, through the streets, but maybe not as much in this existing ditch here. Now, maybe at 10 meters is not a fine enough resolution to see that ditch. They're pretty small. But it's also important to note here where the culvert passes under the road, the tool doesn't know that that culvert is there. It's only looking at the elevation. So this ditch on either side of the road is disconnected. But if that's where the main issues are, I still think the results are useful here. Because if that culvert's backed up, the tool can kind of help show where water may accumulate around the road, which is where it's been closed here by these RV parks. So I better slowly switch back over to the 1 meter results now. I know that it's pretty fine resolution. Hopefully you can see what's going on here. Really, it's a pretty similar overall pattern, but now we can kind of see individual streets that may have drainage issues. And so again, the 1 meter data is not available everywhere. So I was really only able to download it here for the town of Lakeview. So it took 9 tiles to cover the city, and that data took at least twice as long to process as the 10 meter for the whole county. And so now we can definitely see that that ditch is present here. It's got lower values on the slope and higher values within it, but it still looks like there could be more accumulation here in these fields to the north of the ditch, as well as maybe problems, backing up here on the east side of that problem road again. So lacking any verification data, I've never been here to Lake County. I chose to use kind of some simple statistics to set that threshold value of 0.4. Basically, that was 2 standard deviations above the mean of 0.25. So I set that as a threshold value to kind of have this binary raster here, and then added it to a 3D scene with some vertical exaggeration. So I'll try and move this real slow here, bear with me. Basically, we're looking at that same area, but now to the east towards Bullard Canyon. And so this red cone here is marking that problem road. This light blue line is that existing ditch. So just kind of a quick reality check, setting the threshold value at 0.4 kept these wastewater ponds separate. If I lowered the threshold value, they kind of all merged into one. Basically, this you can just kind of see how then water may interact through the town. An important limitation is that the tool uses bare earth DEMs, not a digital surface model. So it doesn't know that these buildings are here, it doesn't have those elevations. So it can't really account for them. But in terms of a quick visualization, I think this could still be useful to kind of see the overall patterns here through the town. So I better start wrapping up here. So overall, I hope, I've got a practical and versatile tool here. It takes an established method, it expands on the results with some more options. Really that's what draws me to the GIS field, not necessarily being an expert in something, but being able to use data analysis, visualization to help support others. So hopefully that's what I've done here. I think the tool's power really lies in it being shareable and expandable. It's going to be fully available here on GitHub. The repo is set up, but maybe don't check it yet for another week for me to finish up. But yeah, hopefully people will check it out, expand on it, improve it, because there are certainly limitations in the methods. Again, it's a simple measure of overland flow. It doesn't account for rainfall, flood timing, flood depths. Again, it can't really incorporate stormwater infrastructure. And really, my study area, there was some confirmation bias because I was using the results to then kind of go back and look for the problems. But I still think this could be useful for Lake County in terms of maybe inventorying all those ditches and culverts and trying to prioritize maybe which ones need to be studied further or replaced. And then there's certainly a lot of functionality I would add to the tool with more time, being able to look at buildings data, maybe being able to convert those results to polygons, and maybe a super stretch goal of making everything open source to get it out of, that Esri environment. But for now, that will do it for me. Here's a list of my image sources. Here you can find me online. And yeah, thank you so much for coming out. Let me know of any questions.